Imagine stepping outside the relentless march of your own life, witnessing the birth of a star or standing on the shores of an ancient ocean. This is the promise and peril of time travel. It whispers to our deepest curiosity, but also carries a profound weight. To tamper with time is to pull at the threads of reality itself. The very thought feels like a violation of nature's laws. We live our lives in a straight line, but what if that line could be bent or broken? The idea brings both awe and fear. What if changing the past erases our existence, or creates a worse world? Time travel is more than a scientific puzzle. It's an existential dilemma that forces us to confront our place in the universe. The power to travel through time would make us like gods, but with unbearable responsibility. So on this day, July 20th, 2025, we stand in our own time wondering, is it possible? Could we ever break the chains of the present and master our own timeline? Long before equations were meticulously crafted and scientific principles understood, storytellers, with their boundless creativity, dreamed of time travel. They spun tales of journeys through the ages, a fantasy woven into our culture for generations, passed down through whispered words and cherished stories. Time travel at its heart is the desire to right wrongs, to undo mistakes that haunt us, see lost loved ones, to relive precious moments that have slipped away, witness history unfold before our very eyes, or glimpse the future and the possibilities it holds. H.G. Wells' The Time Machine, a cornerstone of the genre, imagined a leap far into a strange, divided future, a chilling reflection of societal inequalities. It served as a stark warning about humanity's potential path, a cautionary tale etched in time. Stories like these, with their captivating narratives, made time travel feel tangible, almost within reach, shaping our collective dream, fueling our imagination with endless possibilities. On screen, we watched a teenager in a DeLorean, a time-traveling car that became an icon, nearly erase himself from existence in Back to the Future, a humorous yet thought-provoking exploration of temporal paradoxes, and a cyborg relentlessly alter the past in The Terminator, a dark vision of a future war waged across time. These tales, while fantastical, explore real paradoxes and potential dangers, the intricate web of cause and effect, acting as cultural thought experiments, allowing us to grapple with complex ideas in a safe and engaging way. They make physics personal and thrilling, transforming abstract concepts into relatable human experiences, reflecting our innate curiosity and the universal hope for second chances, for a chance to rewrite our stories. We are not content to be passive observers of time's relentless march. We question its nature, regret its passing, and hope for the power to shape it. These stories are more than mere entertainment. They're modern myths, echoing ancient tales of gods and heroes who defied the boundaries of time, preparing us, perhaps subconsciously, for a future where the lines between science fiction and scientific fact may blur beyond recognition. Our enduring fascination with time travel reveals our deepest desires to understand our origins, to unravel the mysteries of destiny, and to control our fate. Through fiction, we explore the potential consequences, both intended and unintended, of meddling with the delicate fabric of time, all from the safety of our imagination, where the only limits are the boundaries of our creativity. The concept of time travel has captivated our imaginations for generations. But before we delve into the possibilities, and perhaps the paradoxes of journeying through time, we must first ask ourselves a fundamental question. What exactly time? What is its true nature? For centuries, time was perceived as a universal constant, an unchanging backdrop to the events of the universe. It was thought of as a great invisible clock, ticking uniformly and relentlessly everywhere in existence. In our daily lives, we measure time by observing change. The Earth's rotation on its axis gives us days and nights, marking the passage of time in a familiar rhythm. And the Earth's orbit around the Sun gives us years, painting the world with the changing colors of the seasons. But the reality is that our clocks, whether digital or analog, only track the of time, not the fundamental essence of what time truly. So is time a real dimension, a tangible aspect of the universe? Or is it merely an illusion, a construct of our minds, born from the way we perceive and remember events? Modern physics offers a far stranger and perhaps more profound view, that time is not separate, but rather the fourth dimension, intricately woven into the fabric of reality. It's inseparable from the three spatial dimensions, together forming what we call space-time. Imagine space-time as a vast, flexible fabric, a cosmic tapestry that underlies all of existence. Within this fabric, every event, from the smallest particle interaction to the grandest cosmic collision, has a specific place in both space and time. In this view of reality, the past, the present, and the future all exist simultaneously, existing within the complete block of space-time, a static, four-dimensional structure. Our perception of time as flowing is simply because we, as conscious beings, are moving through this block in what seems to be one direction. This perspective naturally opens the door to the tantalizing possibility of time travel, because if time is indeed a dimension, then why are we seemingly restricted to moving through it in only one direction? Why can't we move through it as freely as we move through space? The most compelling answer to this question lies in the concept of entropy, the fundamental law of thermodynamics that dictates that order always tends to give way to disorder over time. We can easily scramble an egg, but we can't spontaneously unscramble it back to its original state. This unidirectional increase in entropy is what defines the arrow of time. And it seems that entropy, this relentless march towards disorder, is the primary reason why we only experience time as moving inexorably forward. The long-held idea of absolute time, a universal constant ticking away uniformly for everyone and everywhere, was shattered. It was a concept deeply ingrained in classical physics. This paradigm shift was brought about by Albert Einstein's revolutionary theory of relativity, a groundbreaking work that redefined our understanding of space and time. Time, he elegantly showed, is not absolute but relative. It's a flowing river, its current affected by motion and gravity. Its passage depends entirely on your speed relative to other observers. The faster you move, the slower time passes for you compared to someone at rest. Imagine two people moving at different speeds, one strolling leisurely and the other sprinting at full speed. They will each experience time differently. Their clocks, if precisely measured, would show a slight discrepancy. And as you approach near light speed, minutes for one person could stretch into hours, days, or even years for another, creating a dramatic divergence in their timelines. But Einstein's general relativity went even further, introducing an even more mind-bending concept. It posited that gravity is not merely a force, but rather the warping of space-time itself caused by the presence of mass and energy. Imagine placing a heavy ball on a stretched rubber sheet, causing it to sag and distort. This is analogous to how massive objects warp space-time, creating curves and indentations that dictate the paths of other objects. Objects follow those curves. This warping effect means that gravity bends not just space, the three dimensions we are familiar with, but time itself, the fourth dimension. The stronger the gravity, the slower time passes. So, stronger gravity means slower time. This isn't just a theoretical concept, it is measurable with incredibly precise instruments. In fact, GPS satellites' clocks, orbiting high above the Earth, tick faster than those on Earth's surface due to the weaker gravitational field, and these differences must be constantly adjusted for accurate positioning. With these revelations, Einstein's theories moved time travel from the realm of science fiction to a topic of serious theoretical possibility, sparking the imaginations of scientists and storytellers alike. If time, as Einstein showed, can be stretched and squeezed like an elastic band, influenced by speed and gravity, perhaps it can be looped back on itself, creating closed time-like curves, maybe even allowing a path back to the past, a concept that has fascinated physicists for decades. In essence, the door to time travel was opened, at least conceptually, by Einstein's groundbreaking work. Even if Einstein himself remained cautious and somewhat skeptical about the implications and potential paradoxes of time travel, he laid the foundation. The blueprints for a time machine, at least in theory, were drawn, inviting generations of scientists to explore the possibilities and challenges of manipulating time. Time is not constant or immutable. It can be manipulated, albeit perhaps within certain limits, by speed. And by gravity, the very fabric of space-time can be bent and shaped. The fundamental question then became, how far can we push these effects, and what are the ultimate consequences of tampering with the flow of time? Thanks to Einstein, we know traveling into the future is not just possible. It's inevitable. We all move forward in time, but relativity lets us change that rate. At near light speed, time slows for the traveler compared to those left behind. Imagine an astronaut traveling at 99.9% the speed of light. 5 years for her could be centuries on Earth. She'd leap into the future, leaving her world behind. This is scientifically plausible. We see it in particle accelerators, where fast-moving particles live longer. The challenge is engineering. A ship near light speed needs unimaginable energy and protection. So while a journey to the future is possible, traveling to the past is far more difficult. Moving forward in time is just changing your pace. Going backward means reversing the flow of causality. It's the difference between floating faster down a river and making the river flow backward. The laws of physics seem to resist reversing time. The future is open, but the past remains elusive. To reach the past, we need more than speed, we need a shortcut through space-time. Enter the wormhole, a hypothetical tunnel connecting distant points in space or time. Imagine folding paper to bring 2 points together, then punching a hole through this is a wormhole. If one mouth of a wormhole travels at high speed and returns time, dilation means its clock lags behind the stationary mouth. Step into the future mouth, emerge from the past 30 years back in time. This is the most plausible time machine scientists have imagined, but the challenges are immense. We have no evidence wormholes exist, and if they do, they'd collapse instantly without exotic matter to keep them open. Exotic matter would need negative energy, a property we're not sure is possible. Another idea, a massive spinning cylinder could drag space-time, creating loops to the past. But an infinitely long cylinder is impossible, making this a thought experiment. These concepts push the limits of physics and imagination. The path to the past is filled with theoretical hurdles. Suppose we build a time machine and step into the past. Now we face the paradoxes of time travel, the grandfather paradox. What if you prevent your grandparents from meeting? If you're never born, how could you go back? This contradiction challenges causality, the rule that causes precede effects. Some propose the Novikov self-consistency principle. The laws of physics prevent paradoxes. You can visit the past, but you can't change it. History is fixed, and your actions were always part of it. Another idea is the many worlds interpretation. Every choice creates a new parallel timeline. Change the past, and you branch into a new universe. Your original history remains untouched. You become a visitor in a reality you created, avoiding paradox but raising new questions. These solutions are fascinating but unproven. The universe may have built-in defenses against rewriting history. Paradoxes remain a formidable barrier to time travel. The logic of time is as challenging as its physics. So, is time travel possible? The answer is as elusive as time itself. Traveling to the future is grounded in Einstein's relativity, but the engineering is daunting. The challenge is not if, but how. Travel to the past remains shrouded in mystery, requiring exotic matter and facing logical paradoxes. The universe seems to resist tampering with causality. Some physicists believe a deeper law will ultimately forbid backward time travel. Others suggest solutions may be as strange as the problems. The quest to understand time travel pushes the boundaries of knowledge and forces us to ask, what is reality? For now, we are prisoners of the present, but humanity always dreams of what lies beyond. Will we one day sail against the current of time? Only time will tell.